Hey, welcome back. Now in this lecture I want to discuss data structures or structs. In previous lessons we discussed arrays, which are used for storing data elements of the same type. So you can have an array of integers or floats, for example, and every element within that array is then going to be of that specific type, integer or float. Now within a struct is a user-defined type, and within that we can store different data elements of the same or of different types. We can actually also have functions associated with that particular struct that can then operate on that particular type. So these are also types similar to what a variable is, and we can instantiate those in the same way that we can instantiate or create variables of a specific type. So the fundamental types. For example, you can have int x and y, so two variables of type int, and here we can have two or more variables of a user-defined type. In this case, the user-defined type will be of type struct, and in future lessons we will also discuss how we can use classes, which is very similar to structs. But so basically, again, a struct allows us to use data elements of the same or of different types, whereas the arrays that we discussed previously would store data elements of the same type, alright? So let's try to define a struct. A struct is a user-defined composite data type or compound data type that can store one or more variables of the same or different types. It is also referred to as a record in computer science. So the struct is stored in a contiguous block of memory, as for the array that we discussed previously. Now we won't really use the term composition, that is the act of defining a composite or compound data type. I will simply describe it as defining. So we are defining a user-defined type, we are defining our own struct. So you might be wondering, what about declaring a type? Well, there are some differences and we'll discuss those as we go along. So we can, before we declare a type, but typically we will go ahead and define a type before we use it. That is, we will define or compose what the structure will look like, what the variables are that are stored within that type. So basically what the layout of the data will look like. And again, in future lectures we will talk a bit about what a declaration will look like for this and where that is useful. Alright, so let's talk about the definition of a struct. The struct type name typically begins with an uppercase letter. This will be the case for all of our custom types, structs, classes, as we'll see in future lessons, and so on. And this is to differentiate our custom types from predefined types, such as int and float, for example. The variable names will, however, use camel case, as with the variables as we have discussed so far. Now that is up to you. Some programming languages and some frameworks recommend Pascal case for your variable names. So that is going to be up to you. That is going to be up to the company that you work for, the framework that you use. So you'll have to stick to those conventions. We will discuss conventions in more detail in future lessons. But for our purposes, we will use camel case for the actual variable names. But for the type names, we will use Pascal case. So the type name or the identifier for our structs is referred to as the structure tag, which can be any legal identifier name, as we have discussed before with functions and also with basic variable names. Okay, so simply a legal identifier name. For your struct type name, do not attempt to use existing keywords, for example. You will get an error. Always remember the semicolon at the end of the struct definition. You will notice where we have the closing curly brace to end the body of the struct definition. You will notice that we end that off with a semicolon. I will talk a bit more about why that is in an upcoming slide. So here we have the basic layout of the struct. We have the struct type name. This is the name that you will write out when you instantiate the particular types. And so in the example where we have an integer, for example, int x, instead of using int x, you will use your struct type name followed by the actual variable name. We will see some examples shortly. Then you can have some members or fields. In this case, we have two members. We can also have member functions associated with our custom types. In this example, we have some toString member function which can print out hello from struct name, for example. Member functions are also referred to as methods in other programming languages such as C#, but in C++ we are going to refer to these as member functions, alright? I will demonstrate member functions in the next lecture, making that easier to reference as well. So let's move on to a more abstract example. As I mentioned previously, we have entity modeling, so we are modeling real-world things with these objects. So throughout the rest of the module, I will typically use this entity for our custom types, so structs and classes. It is nothing specific, it is simply a high-level entity or thing, some abstract thing, and that is simply where I want to demonstrate specific C++ features to you without going into a specific example. This will typically be followed by more specific examples, so examples sometimes related to game development. For example, I will use the vector structs, which typically has 2 or 3 components, whether it's a 2D or 3D vector. We will see that shortly. So again, this is a typical example that I will use struct entity, and then typically I will use some member, so int member, for example, as the member or field. That again is simply because we are not working with a specific example here. It's just some high-level example to demonstrate some C++ feature. In a future lesson, we will discuss constructors, which are special member functions that allow us to initialize the instances of our structs and classes and basically do what we want. We can actually print things out to whatever we want, as we can in regular functions as well. But for this lesson, we will be using brace initialization with a comma separated list to initialize the members as they appear in the definition of in the body of the struct. That is similar to how we would go about initializing an array. Of course, we don't use the subscript operator. So again, we can use braces and a comma separated list of arguments basically that will be passed in and used to initialize the members. Just a few notes on this, however. We can declare a variable, so we can instantiate a struct and simply give it a name. In that case, it will use basically a default method of initialization. But in this way, of course, we do not have a default initialization for our members necessarily. You can actually provide default values, and we will discuss those in upcoming lectures. But with this first example, you need to make sure that those members are initialized properly, otherwise they can contain garbage. You can also use brace initialization, that is preferred. As I mentioned, you can have a comma separated list of initializers. You can also use parentheses and pass in the initializer, but as you can see in the final example, this syntax can be confusing to some students, so that is why I'm emphasizing that here. If you do not intend to initialize on construction, then do not use the parentheses, because as we can see here, this is going to declare a function which returns the type of entity, so that is not what you want. It is going to expect a body, so a definition later on in the code, for example. If you go ahead and use entity2 later on in your code, and you may expect it to behave like a variable, you may get errors along the lines of expected class or struct or something like that. So it can be confusing, and for that reason it's best to sort of avoid this sort of initialization and stick to the brace initialization instead. Or again, in the case where you do not provide initializers, just leave the identifier, the instance name as is, do not provide parentheses nor braces. But again, in that case you need to ensure that your members are initialized properly, otherwise they will contain garbage. Okay, moving on, let's talk about the instantiation and usage of a struct. As I mentioned before, instead of having int x, int y, and so on, we can declare a variable instance or object of our type entity, for example, our custom struct type. Notice the usefulness with our conventions here. We have the Pascal case for our custom type entity, and then we have camel case for the actual instances. So we have entity, and then I'm instantiating entity1, for example. This also allows us to instantiate that without having to number the variables, for example. So you can have entity instead of entity1 because of the differences in the case. But I'm using entity1 here because we can also declare a variable instance and initialize the member. So we can do that in two ways. We can use parentheses, or we can use list initialization, which I'm doing here with the instantiation of entity2. We pass in 13, and that is going to initialize the first member. From the previous slide, remember we had int member in there, so the member associated with that entity struct will be initialized to 13. Similar to how you initialize the elements within an array, we can initialize the elements within our struct using this list initialization method. So I often refer to instances. That is where we have the variable declaration and definition of our custom entity types, but these are typically called objects. So we have an object, a variable, or an instance of type entity, right? And as we can see, this is similar to declaring and defining a variable of a fundamental type. The difference here is that we are declaring variables of our own custom type now. So now that the instance of entity exists in memory, we can define its members, and we can also access the members using the dot operator. In the following examples at the bottom of the slide, we can see we can do entity2, for example, dot member, and that is how we access that member within the entity, and then we can assign 13 to that member using the assignment operator. So that is how we access that using the dot operator. Similarly, if we want to print it out, we can do cout entity to dot member stream insertion operator followed by endline, and that will print out the value that is stored within that member associated with our particular instance, in this case entity 2. I mentioned previously that we have to ensure that we end off the definition of our struct with the semicolon, and you might be wondering why that is. So here we have an example. We can do struct entity, some custom type. So we are defining some custom type. It has some member, for example, int member, and then we can actually instantiate that within this definition basically. So you can declare instances of the struct type in the struct definition. An example here is the entity instance, so I'm using camel case again. We have the struct keyword, followed by the identifier of our custom type. Then we have the opening curly brace. Then we have some members. Then we have the closing brace, so that signifies the end of the body. Following that, we can put in some instances. So in this case, we have a single instance. This is also a list, so you can have multiple ones here. You can have entity instance 1 or entity 1, entity 2, so forth, separated with a comma. So a comma separated list of objects or instances of this particular custom type of ours, entity. So that is why we end off the definition of a struct with that semicolon. That is following the closing brace because we can put some instances within that. We typically would not do this, however. I'm doing this just for demonstration purposes so you can understand why we have this sort of syntax. However, we will typically instantiate our custom types, our structs and our classes where we actually use those as with the fundamental types, int, float and so on. Of course, we can have multiple members, so here I have a struct vector 2D. We have two floats, x and y. I will often use vectors in the examples throughout this module. We typically use vectors in game development to keep track of the position of some character or some object within our game environments. So you can have 2D games where you are concerned with the x and y position of some object in the world, such as our character, for example. Or if you are building a 3D game, then you can have 3 components for x, y, and z, then also for depth, right? Sometimes you have rotators, you have other things for keeping track of the rotation and for the scale, but for now we are using vectors simply for keeping track of position, for example. And so here we have an example of how we can declare a variable or an instance, in other words an object of type vector 2D, and initialize its members. We write out our custom type name. We do vector 2D. We specify the name of the particular instance or object, vector in this example. Then we can use a list initialization, or we can use parentheses to then initialize that object. We pass in what we want to initialize those members to. In this case, 2 floats separated with a comma, so we have a comma separated list, and we end that off with a semicolon. That is our declaration. We now have an object, or in other words a variable of our custom type, in this case type of vector 2D. Alright, let's begin by defining our struct. We can type struct and then follow by the name of what we want to call this type. Now we can actually type out struct and then press tab. So in this way we get a template with a default name, basically a template name that will be highlighted and selected. And so now we can type and give this the name of the type that we want. So in this case we want our struct to be called entity. We want this to have some member to experiment with, so I'll give that a member, in this case of type integer, and I'll name that member. Again, it's important to ensure that the definition of the struct that is following the body of the struct, that we end that off with a semicolon. So in the main function, how do we declare this now? How do we instantiate an instance or a variable of type entity? Well, we use that type name entity followed by the name of the instance or variable. In this case, let's just call it entity. And with this, we can see the usefulness of using the different types of cases. So we have Pascal case again for struct names, and then for the instances or variables themselves, we use camel case as we have before with the fundamental types. Now, how do we modify the members? So how do we assign values to the members of that particular instance? Well, we use the instance name, in this case entity with the lowercase, that is the variable name, not the type name, entity, and we use the dot operator. And in this way we can access the particular member. In this case, the member is actually called member. That is an integer, so we will assign some value to that. In this case, I'll assign 13 to that in that statement or for the semicolon. Then for a quick exercise, I want you to pause the video and attempt to access that member and write that value out to the console, so in a cout statement. Alright, let's just continue on here. We can do cout, and to access that, again we do entity dot, the dot operator, followed by the particular member. In this case, the member's name is actually member as well. And then end line again here, and we can build and run, and that will print out 13. What should happen if we were to print that member out before we actually assign to it? So let's copy that line 15, and paste it here in line 12. We try and access and print out the value of that member. Well, we actually get an error here, uninitialized local variable entity. So basically the member of that particular instance is not initialized at that point in program execution, so we will get an error. It contains garbage. So what we can do is we can use the list initialization using braces. This is similar to initializing an array. So we can pass in some value for that first member, in this case member, the integer member, and we pass in 0, for example, build and run, and we get 0 and 13. So hopefully this is not too confusing. I will remove this code here. Again, this is similar to declaring and initializing integers, for example, or one of the fundamental types. Let's go with int x and y here, for example. We can use brace initialization to initialize those variables. We've seen also with arrays, we can initialize the array using the list initialization, which also uses braces. And so in a similar way, we can declare or instantiate two objects or variables of type entity, also using the comma operator. So we have entity1, we initialize that member to 0, and then we can also have entity2, for example, pass in 13 as an example for the initialization of the member that is associated with that particular entity, entity2. So if we print out entity2 now, entity2.member, then we will get 13. So hopefully this helps to illustrate that the member variables are associated with a particular instance of your struct. So in this case, our struct is entity. Let's look at an illustration of this. So in the main function, I instantiate entity, which is a struct. It has an integer member. I instantiate that twice, so I have entity1 and entity2. So at this point in program execution, these are instantiated. They exist in memory in a space called stack. So we have the main function, and then those two exist now on the stack. Now, of course, with a variable, so an instance of a fundamental type, such as float or int and so on, once that variable goes out of scope, so in this case the scope is within the main function, and when we go out of scope is when we return from the function, or in the case where program execution reaches the closing curly brace, at that point the variable is then destroyed and removed from the stack. Now a similar thing happens with an array. Let's say you have 100 variables in an array an array of integers, for example. When that goes out of scope, so the function returns, the loop exits, so program execution goes out of the body of whatever you have that array in, then that array and all of the variables in that array are basically destroyed, so that memory is cleaned up and we can use it again for something else. In future lessons, we will actually learn about another memory location called the heap, and in that way we can manually manage the allocation and deallocation of memory. But this memory is managed automatically, where again we have memory allocated on the stack within a body, such as again in a function and in a loop. So once these are instantiated, each one of those entities that are now allocated on the stack own an integer member, and the idea with object-oriented programming with our structs and classes is that they manage their data and their members, so the allocation and deallocation of their data. So here, as with a fundamental variable or as with an array, once program execution reaches the closing curly brace of a function, or exits a compound statement, or the function returns, those entities, entity1 and entity2, those instances are destroyed. They are deallocated, and the memory that is allocated for those are destroyed, or in other words erased or cleaned up, and that memory is then available again for us to use later on in the program or by some other program, okay, by the rest of the system. And then actually just to illustrate here, when the function returns, so in this case main, when that returns, and that is also then removed from the stack, that is popped off basically from the stack. You can have a stack of functions, and in this way you pop functions off from the stack, and in this case when main is removed from the stack, of course our program will exit. Alright, so this was just to illustrate that in object-oriented programming we want our instances to manage their memory, and that becomes a bit complicated once we work with pointers and references, as we'll see. But for now, once we have these regular variables, they are destroyed automatically when that particular instance goes out of scope. So the data associated with that particular entity gets cleaned up. This is also to illustrate that each instance has its own data associated with it. Alright, so entity 1 and entity 2 are independent, and they do not necessarily have the same value stored in their member. So they are independent, they are cleaned up independently as well. So again, these are instances of a particular type. In this case, our type is an entity, and that is a struct. For a quick exercise, I want you to define a vector2d struct with two members, float x and float y. Then in the main function, I want you to instantiate the vector2d struct and use list initialization to initialize the members. Then I want you to print those members out to the console. So you can print something out along the lines of my vector has the following members x and y, and then print out the values that those members have. So in other words, you will be printing out the state of that object at that particular point in time in program execution. Alright, so go ahead and give that a try, and when we come back I will step you through that. Okay, let's go and define the vector2d struct. I will begin by removing these lines of code and then also the struct. I will type out struct again and then press tab so we get this templated code. That template identifier should be selected, so I will start typing vector, and I want a vector2d here since it will have two components. For this example I will choose float instead of int, since typically with 2D games or 3D games you typically work with doubles, for example, or some floating point value. That is to keep track of your location. So we have float x, float y. Now how do we instantiate this vector now, this custom type? Well, we use vector2d, that is the type name. Then we can define an instance or a variable of that type. We can use a list initialization, so between braces we can pass in some values here, 13.4 for example for x, and then 15.5 for y. Then in a console output statement I will put out the vector as components, x. How do we access that? Vector.x. Notice that as we type out the dot, so we do vector, the dot operator, then we get a list of the members. And this is a feature of IntelliSense, and this is a very handy feature, especially once you have many members. Of course, your members can have long names, not just x or y. You can also have member functions, as I mentioned. We will talk about that in the next lecture. And this makes it faster to select those. You can just start typing the name. It will filter, and then you can just press tab to select that particular member. We will look at this again in the next lecture. And the same for y. And if we build a run, we get that printed out as we would expect. So as we can see here, we can use list initialization using braces and a comma separated list of values, as we can do with arrays. And in this way we can initialize the members that are within a struct.